Okay, ladies and gentlemen, let's get going. Are there any comments or questions about anything so far? Any comments or questions about anything at this point? Presumably you've gotten into this week's lab assignment. I hope you find it a little more interesting than last week's lab assignment. It's actual problems that actually kind of do things. It's not bad, second week of the term. Any comments or questions about anything so far? All right then, so let's see where we are. We've seen this formulation before, right? We have things and we have actions, and we categorize those in various ways. What I want to talk about today is that modern programming languages are extensible. That is, program can define new data types. We've seen that already with name tuples, right? If we define a name tuple to represent a student, once we've done that, we have a student type in our program. We can build student type things, and we can do operations on student objects, and it's as though we have our own special customized programming language that has all the things that Python has, plus students as a data type. So we've seen extensibility for data, and we'll see more as we go along how we can combine the data structures we have into more and more rich and realistic structures. But we can also define new operations. And that's what we're going to do today. So we can aggregate data into a package and deal with the whole package at once or the individual pieces of the package. That's what we've done with name tuples. We can do the same thing with statements or operations. We can package them up and give them a name. Now, the form that these extended operations take will be functions, right? In Python, you can't make up a new symbol to mean a new thing. Not easily anyway. Some programming languages let you do that, but Python doesn't. So you can't easily create whole new statements. You can't easily create new symbol operators. You can create new functions, and that's what we're going to do. You can also create new methods, but we're not going to talk about defining methods in this class. The idea is just the same, but that goes with class definitions, which we're going to put off till ICS 32. Okay, so the new operations we're going to define are in terms of new functions. Now, the next thing we're going to do is develop a little bit of vocabulary for talking about features in a programming language. Right? Anytime you have a feature in a programming language, there are two things you need to know. You need to know how to say it, and you need to know what it does when you say it. And so in linguistic and programming language terms, we say syntax and we have semantics. So we could talk about the syntax and the semantics of an assignment statement. So the syntax of an assignment statement is a variable and an equal sign and an expression. So with this syntax notation, there are two kinds of components, and in this kind of text, we don't have a lot of typographic freedom to distinguish them. But there's the template, the framework, the form, which in this case is just the equal sign. And then there are placeholders that you fill in, which in this case is variable and expression. So, we know that's a variable. That's a variable. This is an expression. An expression is just some phrase that Python can figure out the value of. So for that expression to be a valid expression, the variable hours has to have a value somewhere earlier. The variable rate has to have a value somewhere earlier. And if those two variables have values, then Python can evaluate the expression, figure out the value of the expression by multiplying those two numbers. And then the semantics of the assignment statement are okay? So we know this already. The semantics of an assignment statement are take the value on the right-hand side, evaluate the expression on the right-hand side, and put that value into the box, the variable named on the left-hand side, okay? So syntax, the grammar, how you say it. Semantics, what it does, what it means, right? So any feature in the programming language we can describe this way. And usually it will be clear. Usually it'll be clear what the placeholders are, what, in some sense, the variables in our syntax description are that have to be replaced by an instance. Right? We don't type variable space equals space expression. We have some variable and some expression with the equal sign always being the same. Okay? So, comments or questions so far? This is, except for the term syntax and semantics, I think this is all familiar. Any comments or questions so far? Okay. So, what we need to do is figure out how to define a new function. And so let me give an example first. Okay, so here is a function definition the way we're going to define them in this class. There are some things here that Python doesn't absolutely require. Your TA and we on exams will require them. So I'll show you in a second what the sort of bare bones picture is. But because Python lets you get away without specifying all the things I've specified here, doesn't mean that that's okay. We're following a particular form. That form will help us avoid making errors, right? I mean, it's not just arbitrary for somebody's jollies and kicks that we add these things. But the essence of this function definition is that. So the other things are essential for us as we write these things. They help us write functions that don't have bugs in them. But the fundamental part is what we just see here. And so let me give you the syntax of that. We have def Okay, so when we define a function, we have the name of the function, right? There are predefined functions like square root and len and int and float, things that we've seen already. We pick our own name. We just pick double here because what it does is double the input. And then after the name of the function, we have a list of variables in parentheses. In our example, we just have one variable, n. But we can have more. Those are the inputs. If you think about a function, need some chalk. If you think about a function like a meat grinder, right? You put some inputs into the top, and you have a crank, and you turn the crank, and the value comes out the end. So for this function, which is double, we put a value in the top, like 7, and what should come out the spout is 14. So, if you want to think of it concretely like a meat grinder, that's the idea. This is what a function is. We turn the crank, it takes the input, it does what it does, in this case multiply it by 2, and send that value out the end. So there are, all right, let's say two things. We can define a function, which we've just seen how to do. And we also call functions which we can do, for example, like this. We give the name of the function. We give the name of the function. We give its input, what goes in the spout, and then the result comes out at the end. So let's just run this. The only thing we printed is double of 17, which is 34. There it is. Python has read our definition. It actually read the second definition also. But the definition just says, here's what this means. It doesn't say do it. It's like when we call named tuple, when we set up a named tuple, describe what the fields are. That just tells Python, be ready. Right? Here's the blueprint. Right? The first time when we say, book equals name tuple, book, author, title, price, year, right? That doesn't build any books. It just builds the blueprint for a book. And then if we want to build an individual book, we call the book constructor book, War and Peace, Leo Tolstoy, blah, blah, blah. Okay? So same thing here. Defining something, just make sure Python knows what you're talking about when you use it. And then calling is when we actually use it. So we're calling the function twice down here, and we could display the value of x, which is what we expect. Okay, so there are a couple of terms to get down here. We have calling a function and defining a function already. The data that goes in the spout, we call the arguments or the parameters to a function. There's a technical difference that we don't have to worry about right now. We use both terms. Or the inputs to a function. Right? Now, the inputs to a function are an entirely different thing from what you get when you do interactive input by calling the input function. Right? When you call the input function, the console waits for the user to type something and hit return, and then the input function returns what the user types, right? I mean, it's the same kind of thing. X is double of 25. Name is input. Like this. This is a function call, right? It's purple because it's predefined, but it's a function call. It has a parameter. We might not have seen this in class, but they do it in the book. This is just shorthand for saying print, please enter your name. Name equals input parenthesis parenthesis. So you can just squeeze that together and put the prompt, what you print before the user types something. You can put that as the parameter or argument or input to the input function. And then so we call the function. Let me put it this way. We call the function returns a value. So using the function, calling the function, that's what we do here. That function takes its argument and returns its value, which is 34, which we then do something with. In this case, we print it. In this next case, we assign the value to x. But both cases, the function, we call the function with the argument. What gets substituted for this is the result of the function. What we say return, what we say to return in the function, that's the value. So we define functions. we call them, the function returns a value, and we use that value somewhere. Right? So a function call, like double of 17, is an expression, just the way 3 plus 5 is an expression, just the way quote ABC, quote, is an expression. Right? They're all things that have a value to Python. The value of the call to the function double with the argument 17, you're getting used to the vocabulary. Right? The value of the call to the function double with the argument 17, the value is 34. That's what the function returns. And so we substitute 34 for double 17, and we print the 34, and that's what we saw. Okay. So defining, calling, returning, using that value in an expression. We haven't talked about the expanded form of a function definition up above. We'll do that shortly, but let me ask first if there are comments or questions about anything else so far. No? It's okay. Yeah. So is the question, are we going to learn how to define a function that has optional parameters?
No, what you said earlier, how we have to define it more than what Python requires.
Yeah, yeah.
So what exactly are those?
Okay, I'll tell you. I mean, well, the requirements are what we see in the second definition of double, but what we're going to do looks more like the first definition of double, and I'll talk about what that is shortly. That was what you wanted to know? Yeah? Okay, so I'll get to that pretty soon. Yeah?
For the first definition where you define double, do you have to specify that the input and output have to be integers?
Well, they don't have to be integers. They can be any type. But do you have to specify? We have to specify, yes. So that's part of our way of defining functions. I mean, it doesn't just belong to me, but it's our way of defining functions, which is the first definition with those various extra lines, and that does involve indicating the type of the arguments, the type of the inputs, and the type of the return value. And I'll talk about that in a minute. Yeah. If you don't, Python doesn't complain, but your TA will complain. Okay? And your TA, of course, I mean, it's not that your goal in life is to please your TA. Your goal in life is to learn how to be a effective, competent, professional programmer. And your TA enforces these various things because they'll help you reach that real goal. Yes? I'll tell you in a minute. That whole thing we haven't gotten to yet. Comments or questions before that? Okay. So the bare bones, the essence, we have def, we have the name of the function, we have the name of the parameter. See, what happens is that real-life software is not usually written by one person. And if it is, you know, it's the person you are when you write it is not the same person you will be 6 months from now when you need to change it for some reason. So, you know, even if it's actually one person, you know, you're going to be a little different, which means you need to write code not just for Python to execute, but also for human beings to be able to read and understand. We probably talked about that briefly before. But you know, getting the code to produce the correct result is important, probably the most important thing. So you don't produce a correct result, you know, what are you doing anyway? But that's just the first very important step. Your code needs to be readable, understandable, because you or somebody else are going to have to modify it someday, because software reflects the world keeps changing, software has to change to match how the world changes. So, I actually forget how we got to this. What was the question that prompted this, whoever it was? So just ask your question again, whoever it was. Oh, I haven't talked about assert yet. That wasn't what I was answering. I was answering the, that's right. Real programs are written usually by teams of people. And real programs are hundreds of thousands or millions of lines of code long, divided into pieces. And one person or one team will work on one piece, and another person, another team will work on another piece. You can imagine that nobody would get any work done if all the 100 people on the software development team had to make sure that nobody used the same variable name in two different places. Right? You have a million lines of code, and somebody gets to use X and nobody else, and the rest of the million lines of code gets to use X. You'd have interminable meetings just to agree on who's going to use what variable names. Well, programming languages give you a way of sort of limiting where names are known, so that normally you use the variables that you use in your own part of the code, and somebody can use the same ones in their own part of the code, and they don't interfere with each other. Programming languages keep that straight. We'll see examples of that as we go along, but the reason that we have a name here for the parameter n is that we can use that name in the body of the function. We can use that name in the body of the function, and Python keeps it straight, so that if we have some other function that has a parameter named n, when you call that function, you get that n. When you call this function, you get this n. And there's no need to sit around the water cooler and agree about who's going to do what. So again, schematically, 7 goes into a variable inside the function called n. And inside the function, we talk about n, and that's just whatever value we happen to put in the top. So when we called double with 17, 17 is the value of n inside the function. When we call it with 25, 25 is the value inside. Then we multiply that by 2 and send it out the spout. So the return statement says take the expression, and that's the value you kick out the door. That's the value you send out the spout. That's the return value of the function. So we know the syntax. Def, name of the function, name of the parameter or parameters, and then one or more statements ending with a return statement that says return and an expression, and that value probably using the parameter. That value is the value that gets sent back to where you called it from. Right? So we called double from the print statement and the assignment statement to X, 6 lines up there, and there we go. All right, so again, are there comments or questions about the mechanism of defining, calling, returning from a function before we look at the real form of function definitions? Yeah? We could do that, yes. So the question is, could I have as an alternative so could we say it that way? Yes, we could, and it would work also. No particular advantage to doing it the second way, just takes an extra statement, but it's perfectly legal. Other comments or questions so far? Yes?
What was the arrow at the very top?
Okay, that's one of the parts that we're going to get to in a second. That whole block there, I haven't described yet. I'm about to, but I want to make sure everybody's comfortable with the basic mechanics of defining a function in one place and then calling the function and getting the return value, which is then used wherever the function call was. Yeah. Well, the colon is part of the syntax of the define statement. That's really the answer. There's the syntax up there, variable, function name, list of parameters, colon. When you define a function, you put a colon at the end of the def line. There are other places in Python where we have a colon at the end of the line. It kind of signals that there will be some lines that are somehow included in or subordinate to that line. And just from the appearance standpoint, the colon says the next lines are going to be indented. Right? So if you think about it, you have def, you have the function name, you have the list of parameters, you have colon, then you have the body of the function. That's what we call everything that's part of the function. And the body of the function is indented, and that tells Python what statements are part of the function and what statements aren't. So we have, def double, and the definition of double is that return statement, or def double alternative. The definition is those two statements, but that's it. And the definition of double alternative does not include this triple quoted string, or this call a function comment, or the print statement, or the assignment statement to x. None of those are part of the definition of double alternative because they are not indented underneath the def. They're indented back at the left margin again. Okay? So, one answer to the question of why do we have a colon is because that's how you say it in Python. But for function definitions and some other things that we haven't seen yet, the colon is a signal that the next few lines are going to be indented because they're included as part of something, in this case included as part of the definition of the function. Yeah.
Was double ever a keyword?
Double is not a keyword in Python. Yeah. Other comments or questions? Okay. So let's look at the expanded form of the definition of double there. As I say, that's the pattern we're going to follow. It's actually part of something that we call the design recipe. This way. If you go to the course reference page, you'll see a link to a page description of this whole design recipe, and it refers you to that from the lab assignment also, so you can see a more detailed write-up. It's not as though there's a completely mechanical way that you can get your functions defined by just following the steps and not having to think about it. It's not that good a recipe. But it does give you some steps to follow so that you feel less stuck and less rootless and not knowing which way to go. It gives you some steps that help you narrow down the things you need to put the function together, and they help you avoid making a lot of mistakes that can come when you don't. When you're not explicit about what you need to do, right? If you need to be careful about something, it generally involves slowing yourself down a little bit and not just rushing like crazy. If you're driving, if you're driving a truck full of explosives, right, you're probably not going to ride down the freeway at 85 miles an hour. even if it weren't so crowded that were impossible. There are times when it's possible to drive at 85, and people do drive at 85 with some regularity on the freeway. Well, you're probably not going to do that with your truck full of explosives, because you're going to want to be a little more careful and take a little more time to look for people heading towards you and that sort of thing, because it's dangerous. Well, coding is dangerous because it's meticulous and detailed, and it's easy to overlook things, right? I mean, people are not the greatest at doing very detailed precision work. And one of the things that programming languages do for us is come up with features to help us avoid common mistakes that programmers make. Now, sometimes that annoys us a little bit. It means we have to do a little bit of work, and we feel constrained at having to take baby steps instead of being able to walk what we think is normally. But the thing is, if we walk what we think is normally, history shows programmers miss things. Right? And it's not just novices, it's not just new people. Professional programmers, don't write perfect code the first time. Nobody knows how to do that. And so various methodologies have evolved over the 70 years we've had computer programming. Various methodologies have evolved to help programmers get their code correct the first time. So all this stuff up in the first definition of double at the top of the page, it's all there with that in mind. Right? We add some things up front, we're explicit about some things up front, and they help us be confident that our code really works. So, if you're saying, hey, I'm an experienced programmer, I know what I'm doing, I'm not going to screw up, this is for babies, this is part of a professional software development methodology, right? This is not something that's just for students. All right. So, what do we have? What do we have with this definition that we don't have in the bare bones definition? We have this annotation that says what type of thing, comes in the spout, comes in the funnel at the top, what our input is, what kind of thing. That's useful because a common error that you will make throughout your career, but especially this quarter, a common error is to pass the wrong kind of input to a function. And so if we have a book structure and we call double with the name of some book, we're going to come in here, we're going to try to multiply that by 2, and Python's going to say, wait a minute, book isn't a number, I can't multiply it by 2. Error. So if we're explicit about what type of data we're expecting, then we're less likely to pass the wrong kind of thing in. Now, note, right, especially for those of you who have previous experience, saying this it's called in Python an annotation. Right? It doesn't make Python check for you. If you pass in the book, you don't get an error message when you call the function. You get an error message when you try to multiply a book by 2. So when you try to do something impossible, that's when the error message comes. This doesn't add any extra checking by Python, but it does give you an explicit description of what kind of data it takes. It's also useful because you might be writing this function that other people on your project team are going to use. And you need to tell the other people on your project team how to use your function double without necessarily telling them how you defined it, right? That's kind of your business, right? How you built it, that's up to you. And the people who use it don't need to know that, just like you don't need to know the Python code that's behind the square root function in Python. You could look it up, but Python's an open source thing. But you don't need to know that code. You just need to know that if you take the square root function and you give it a numeric argument, it'll return the square root. And so that level of description, how to use it as opposed to how it's built, That's called an API, an application programming interface. We'll see this term a lot. And specifying this is something that we can do. Specifying this is something that we can do to help automatically generate an API. So in fact, let me do this. Let me change this definition of double. Okay, so I'll just name that separately. And I didn't have this at the bottom. Okay, so if I were to say, whoops, right, I've just defined double. Here's the only definition. And Python will automatically pull this stuff out that says it takes one argument that's an int, it returns an int, and what it does in English is return 2 times the parameter. So if we follow this function, one thing we get automatically is this automatically generated documentation that we can then give to whoever wants to use our program. So the annotation of the parameter type, that's the first new thing. This arrow and a type name, that's the annotation for the return type. What kind of thing comes out the spout. And you care about that because that tells you the kinds of places you can use the function double. So I can say 3 plus double of x, and assuming that x is a number, that makes sense because after plus, a numeric, an int value makes sense. If I were to say upper is a function that takes a string, might be a method actually. Let's use sum. Sum is a function that takes a list of numbers and returns the sum of the numbers on the list. So if I were to say print out sum of double of x, I'm going to get in trouble because sum expects to have a list. Double of x returns an int that's the wrong type. So the annotations on the top line, which shows up in purple on the top line of a function definition, the types of the inputs, the type of the return value, those are there partly so that Python can pick them up for the help results, and partly because it makes it clearer to the human reader of the code what contexts you can use the function in. All right. Second line of the function is a string. That kind of string, I mean, it's a triple quoted string. It's a character string constant like any other character string constant. But putting it as the first line in the definition of a function, in Python it's called a doc string, doc for documentation. It's a short one-line description of what the function does. The kind of thing that it would be useful to have, in a brief reference description of how to use the function. So there are a lot of predefined things that we can get help on. And so here, this is a longish list, but here are some methods on lists, like count, that takes a value, returns an integer, and it says what the value is, the number of occurrences of the value in the list. So we have this same kind of documentation for predefined things as we have for the things that we define, and this brief description is good. you have to kind of get past the mindset of you're doing homework for an instructor that nobody else is ever going to see, and think about you're writing code that might be readable or should be readable by other people someday. Not so much of that in this course other than you and your partner and the TA, but in real life, you have these things that you know in your head, but you're not the only person you're writing the code for. Okay. The return statement is the same return statement. That doesn't change. And then outside of the definition, we have these assert statements. They serve two functions. Typically, when we write a function, as we follow this design recipe, when we write the function, we give some examples of what we expect it to return. That helps you a lot when you're actually writing the code if you come up with some examples before you write the code. What should double return when we pass it a 5? What should double return when we pass it a 0? What should double return when we pass it negative 73? Think about those things, about the different kinds of values you might give and what the result should be. Figure it out if it takes a calculator, so that you have examples, and that helps you write the code because you've thought through all the different possible sorts of values, and probably in doing the computation to come up on paper with what you expect the answer to be, probably that helps you figure out how to code it up too, what the steps are to code it up. So before you write the body of the function, you write these examples. In this case, double of 2 should be 4, double of 0 should be 0, double of 1, 1, 2, 2, 2 should be 2, 2, 2, 4, 4, 4. And we'll talk a little bit later on about strategies for coming up with good examples that cover the range of possible values. But here it's kind of any integers. We didn't do one negative, but we could. So we write the examples first to help us write the code. But those same examples, if we write them as assert statements, those same examples can be tests. And what the assert statement does is it evaluates the expression, right, which is a Boolean expression. It's going to be either true or false. And so if the expression is true, if double of 2, when we actually call double, is equal to 4, that's fine. The assert statement doesn't do anything. It shuts up, keeps on going, checks the next one. Right? If double of 0 equals 0, if that's true, no problem. Double of 1, 1, 2, 2, 2 equals 2, 4, 4, if that's true, no problem. If I have one that's wrong, now, it could be wrong for two reasons, right? It could be that I calculated the answer wrong, or it could be that the function's wrong. It's going to be a little easier for me to get the answer wrong than to get change the function so that it calculates something wrong. But the result is going to be the same. Okay, so that's wrong, right? Double of minus 18 should be minus 36. So if we run this, we get an error. On line 38, assert double of minus 18 equals 36. Assertion error. So that says, hey, you had your test. You said it was supposed to come out 36, and it didn't. So now we know that there's an error. Right? In this case, the error is in our test, not in our code. We hope that we get our tests right so that it's just the code that we have to look at to fix. But now that should work. And there we go. Okay, so it was just silent. Why is it good for the assert statements to remain silent when everything is okay? Because you can leave them there. Remember, this code is going to change someday. Maybe not so much in this class, but real code changes. So once you've gone to the trouble of having the tests, let's keep them there, keep them in place, like an always vigilant sentry. Every time we run we go through the file and do the definition, we'll do these assert statements to test to see if everything's still working. Because sometimes in programs we make a change in one place and it produces the wrong result somewhere else. If you're worried, those of you maybe with a little experience are worried about the efficiency aspects of that, there's a way to avoid that. There's a way to only do the assertions when you're testing and not when you're actually running. So you don't have to worry about that. You're being stuck with that permanently. But leaving in the code the tests is good because it helps you know if you've broken something later. And it also is another way of documenting or describing what your function does, because you have these examples there that illustrate what's supposed to happen. Okay, so when we write functions, we're going to write them in the form at the top of the page with annotations of the types of the parameters, the type of the return value, with a docstring comment, one line that says what the function does, and with assert statements that indicate what results we expect, which, when we run the code, will check them and let us know if there's a problem. Okay. Other comments or questions? Yes, go ahead.
For the parameter annotation, if you were doing something with multiple parameters, would it be parameter 1, colon, type 1, comma, parameter 2, colon, type 2?
Yes, it would. So let me just let me do it this way. Okay, so yes, if we have more than one parameter, we separate them with commas. When we're doing annotations, the annotation comes after the parameter name and before the comma. Okay. So that was a good question. Thank you. Okay, good. Other comments or questions so far? Yes.
Said that it doesn't check the parameter data type, does it also not check the return data?
Yes, Python doesn't check at that point, right? So if we do, it checks when you do something impossible, but putting the annotations doesn't make Python do anything. Now, as it turns out, it's possible for you to write programs that do that checking. Right? And if you follow us along through to ICS 33, I think that's an example or an assignment where you actually get to do that, where you get to take annotations in that form and write code yourself to check to see whether the types match the annotations. And if you think about it, we sort of know the essence of how to do that because we saw the predefined function type, right? Type, parenthesis, some argument, tells you what type it is. And so if we can do that in our program, we could run tests to check that. We haven't learned quite how to do that. But the fundamental thing of examining something to see what type it is, we've seen that that's built into Python. So it's doable, but we're not doing it in this class. Yes?
In the function, two-parameter functions, after the arrow, so it's string and then integer, or just string?
Just string, right? So functions typically have one return value. Now that one return value could be a list, or it could be a name tuple, or it could be other things that have multiple components, but it's one package. So there are kind of ways of getting around that, but normally, if that's what you're thinking, you've probably confused something. So think about functions as having perhaps many inputs, many parameters, but one return value. So there's always just one thing after the arrow if we're annotating that. Yes?
If it doesn't check the return type, can you have like short description of what it returns?
Well, Yes, you can, although I would maybe put that in the doc string instead, but it would be legal, since the annotation can be any type. Accept that. Okay, so I can put a string here because I'm allowed to put any valid Python here. So I could do this, but we don't usually use this for semantic documentation. We'd probably put that in the doc string instead and just say that it returns a float. But it is legal to do that if you want. Sometimes we do that if we're saying that it returns a particular kind of list, right, like a list of books or a list of students or something like that. Sometimes we'll just put that in quotes because there's no nice annotation for that. Yeah, thank you. Other, yes? Yes. So annotations like comments don't tell Python to do anything in particular, but human beings read them and get information from them. That's exactly right. I mean, except that the annotations are picked up when we do the help. So the annotations show up. The annotations show up in this kind of documentation also. So that part of Python pays attention to them. Yeah. How many assert statements do you need? You need as many as it takes to demonstrate to yourself and anyone else that the program works the way it's supposed to. So, maybe the 4 we have here is pretty much enough for something as simple as multiplying something by 2. But, we'll see some examples where we might want, half a dozen or a dozen or something, depending on how complicated our functions are. Normally, we try to keep functions small so that any given function doesn't need a ton of assert statements. But if a function does something complicated or has different categories of inputs that can happen in combinations, we want to try all those different categories as testing, or we won't know for sure that our program works. We won't be as convinced that our program works. Other comments or questions so far? Yes? No? Okay. All right. So let's do something else. All right. So I've shown you the normal or basic form of a function definition. That is a function that calculates some value and sends it out the spout, and we call that function somewhere in our code where that value can be substituted for the function call, right? Our code says double of 17. We get that computation, we get 34, and the 34 goes in the code where double of 17 was. I mean, in Python's head, right, it says double of 17. Okay, that's 34. I know how to do double. That's 34. And then that 34, we do what we do with it. We print it out. We use it in another computation. We use it as an argument to another function. But anywhere we can put a number, we can put a call to a function that produces a number. And that's what we do. So sort of, I would say the way primarily to think about functions is functions having inputs and a return value or a result. Now, we already know two functions, or a function that violates each of those. Right? The print function takes inputs but doesn't have a spout. It just prints stuff. The input function takes no inputs but does return a value, namely what the user types before hitting return. So it's possible to have these other kinds of things, but they're unusual. Right? And most of the time, when we write functions that have inputs and produce outputs. And then we can hook those up together, right? So the output of this function can be the parameter to another function, and so on. So these are functions that return a value. But it is possible to write functions that have side effects instead. Okay, so the print function is an example. It has a side effect. It produces something over here in the transcript window. There are functions that do graphics like the ones in the lab this week, right? The function that draws, or the series of functions that draw the x, they all have side effects, right? Of creating a canvas and putting the graphics in the canvas, and they don't have return values. So there are certain kinds of things, certain kinds of circumstances where that's the sort of function that we want. For our purposes, the problem is pretty much always going to tell us what kind of function we need. So, this, deciding when to do which, you don't have to figure it out for yourself most of the time. If you read the problem description carefully, it usually just tells you. But let me give you an example just so that you can see it. So let's try this. Multiplication for strings gives you that number of copies. So we have a string here with an asterisk in it. 10 times that is this, a string of 10 asterisks. We'll see that in a second. And this kind of function that has a side effect doesn't really have assert statements, right? There's no Boolean expression, true or false. There's no way of saying, did I just print 10 stars, true or false? There's no way to write that in Python. So let me put it this way. So if you're saying, oh, well, I want to write this kind of function to save me the trouble of writing assert statements, you kind of got it backwards. Because if you can't do your testing right there with an assert statement, you're going to have to do testing by running the program a bunch of times and looking at the output, which is more time consuming and harder and longer and worse. So print 10 stars, we can call this, you can, not any surprise what happens. I'm going to do one thing though. I'm going to comment this line out so I don't have to keep typing in a name. All right, so okay, so there are 10 stars. That was from earlier. No big deal. Now, we could make this a little more general. Donald Knuth Okay, so Don Knuth, he's just a name you should know. He literally wrote the book on computer science. He was the first guy, probably 40 years ago now, to try to write a systematic description of what was then a bunch of kind of engineering tricks to make computing work. He science-ified it, and he's retired now, and he's working like crazy on trying to finish up his book. He originally contemplated 7 volumes, and that was 40 years ago. You can imagine how much the field has expanded since then. It's expanded further than one poor professor can run, but he's doing his best. He's devoting the rest of his life to finishing up this master treatise. And one of the things that he said was, computer science is the practice of changing constants into variables. Right? If you have a constant, like in print 10 stars, that's sort of limited usefulness because it gives you 10 stars and that's it. Right? If we could change that constant into a variable, then we could change the value of the variable, and we have a much more flexible program. And so that's what we're going to do. No return value, right? No arrow here, nothing after the word return. And same thing is true Okay, so here's 15 stars, which we got from print n stars, and of course, I can't do it with assert statements, but there are a couple more tests. Right, there's the 15, there's the 0, there's the 3. It looks as though it works. So this is a function without a return value. It has a side effect. It prints. There are other kinds of side effects we can have, like the drawing on the canvas. And we'll see some others as we go. This is all fine. It's legal every so often. This is the way you want to do it. But I'll tell you that your code is more flexible if you turn something like this into a normal function that returns a value, because then the place where you call it can decide how to use that value. Here, we have the stars, and we print them all in one package. Maybe that's just all we're ever going to want to do in our program, and that's good enough. But if we wanted something more flexible, we could define something like this. Now we have a return value. We can have assert statements. That's okay. Now we can say print if that's what we want to do, but we could also say double of 6 is going to be 12. We're going to get 12 stars. We're going to assign that to x. So let's run that. Okay, so 2, 5, or 6. Wait a minute. Oh, yeah, so here we are. N stars of 5. There's the 5. X has 12 stars. I'm not going to count them, but I'm sure it's right. And the assertions all passed because we didn't get any complaints. So we think that this works. So defining a function that returns a value gives you more flexibility because you can use that value in more different ways in the program that calls the function, in a print statement, in an assignment statement, in something else. And it's now amenable to testing with an assert statement because we have a single value that we return that we can check, so we can be conveniently assured that our program, or convinced that our program works correctly. Okay, yes, Wayne back. What happens if n's negative? We just get the empty string. So that's how string multiplication works in Python. If this number is negative, we just get an empty string. It's just the same as 0. That's just what Python does. Yeah?
I have a question about not returning anything.
Oh?
Do you need the return statement, or is it the end of the annotation?
Okay, that's a good question. The question was, if we have a non-value returning function here, do we need a return statement at the end? Do we need a return statement at the end, or what happens if we just leave that out? Can Python tell that that's the end of the function, so there's nothing to do but return? Answer is yes. Python, if you leave it out, Python knows when it gets to the bottom of the function definition, when it gets to the bottom of the body of the function, I should say, it should return, and that's it. Generally better to be explicit about having the return statement, not that big a deal. But there are, it's just a little bit more explicit. It's not that big a deal, though. Yeah.
Can you do it for functions that do have a return type?
No, because you have to say what you're returning, right? So if you're going to send something out the spout, you have to say what that is. So you have to say return blah, and if you leave the return statement out, how does it know?
So there's no default.
There's no default return value because there's so many different kinds of functions for so many different kinds of things. How would you possibly, pick a default that would make sense in a lot of circumstances? Good. Other comments or questions so far? Yes, go ahead. Was there a question?
Oh, why is it that we still need parentheses when we don't have any parameters?
Python needs it to know that it's a function call instead of just a variable. Right? So it uses the empty parentheses to know that the name before it is a function and not some variable instead. So it's Python's grammar. If you don't like the decision, go yell at Guido van Rossum. But there are programming languages that don't have that constraint. But in Python and a lot of languages, function names always have an argument list, even if it's empty. Okay? You can't just use the name without an argument list. Other comments or questions? So, yes, no, that wasn't a question. Okay, go ahead. Okay, so that was the same question was asked before. You can leave out the return statement if it's the last thing. Python can figure out. There we go. Python can figure out that once it gets to the end of the body of the function, there's nothing else to do. It can return. It's probably, as I say, it's probably better to put it in, but it's not that big a deal. Other comments or questions so far? Let me just make sure there's not some other big thing here. Let me show you one more thing in the 2 minutes we have left. It'll only take 2 minutes. Computer science, Knuth said, is the practice of turning constants into variables. Let's generalize n stars into n copies. It's always risky to type some code and test it in the last minute of class, because if it doesn't work, we've got to scramble to fix it. But let's see what happens here. Okay, no complaints. The assertions are correct. We don't have time for more assertions, but I added an extra parameter so that instead of building in this constant of an asterisk, I can pass in the thing that I want multiple copies of. I have something more general by turning this constant into a second variable, a second parameter. Okay, that's it. Thank you very much. I'll see you on Thursday.